Hello, this is João Almeida again. In one past video, I told you about seismic hazard and how it could be expressed by using different intensity parameters. Additionally, I mentioned that seismic hazard was one of the components required to compute seismic risk. In this video, I will tell you about the other components, namely exposure and vulnerability, and briefly explain how they all come together to obtain a measure of seismic risk. I will also give you some examples of databases and tools that are currently available to compute component and risk in general. Seismic risk can be defined as the probability of losses of different types due to earthquakes in a particular region over a future time period. Ultimately, we are interested in developing models that help us estimate the probability of loss due to a seismic event that has not yet occurred. To do so, we need to identify and assess individually each of the components that together make up seismic risk. These components are the hazard, exposure, and vulnerability. The seismic hazard was discussed in detail in week 1. For what concerns exposure, these two photos illustrate the concept. They were taken from the same area, on the left back in 1930 and on the right more recently in 2005. It is apparent that, unlike seismic hazard, exposure can be highly variable in time. Measures of exposure can include the number of people, GDP, buildings, or others, and they are described by groups according to their geographical location, taxonomy, and value. Exposure models are based on global population distribution databases that consider both urban and rural areas. The data sources are censuses and surveys gathered at political or administrative units level. Various geo-referenced global databases exist. They are generated with different methods. The project Gridded Population of the World, GPW, was the first main effort to create a global georeferenced population dataset. Available population data at the lowest subnational administrative unit is assigned uniformly across all the grid cells of the unit without consideration of the type of area, urban or rural. By contrast, the Landscan Global Population Database distributes national populations following a model that takes into account different coefficients of population depending on the type of land cover. The use of aerial photography and high-resolution satellite imagery helps to improve the collected data. This database also considers the average movement of individuals over 24 hours, the so-called ambient population. Finally, the Global Rural Urban Mapping Project, GRUMP, combines the GPW with census and satellite data in order to build higher resolution gridded population data of urban and rural areas. Exposure can also be expressed in terms of the gross domestic product. The World Bank created a global gridded distribution of GDP using GRUMP high-resolution population data. It includes the subnational gross regional product where available. Finally, building exposure models should take into account not only the different characteristic building typologies that can be found around the world, but also at a local scale, as these photos taken from the same city illustrate. The United States Geological Survey Pager system, to which I will come back later in this video, provides a building inventory with residential building stock distributions available for different countries. It uses a variety of sources such as UN Habitat, housing census, published literature, expert opinion, and so on. Finally, reference should also be made to the Global Exposure Database of the Global Earthquake Model, which I will also introduce in this video. The database structure is made for accommodating buildings and people data from the country level to the individual building level. In the first version, the information on people and the number, built area, and reconstruction cost of residential and non-residential buildings is aggregated at a 1 kilometer resolution. Data on single buildings are accessible for some areas. This availability will become greater with time. In a nutshell, exposure expresses the location's characteristics and the value count or area of the assets. We can now address the last component required to compute seismic risk: vulnerability. Vulnerability can be quantified by a vulnerability function, which describes the distribution of loss, such as fatalities or repair cost, with increasing intensity measure levels. I recall that such intensity measure levels express the seismic hazard as discussed in week 1. When sufficient data is available, vulnerability can be further disaggregated into fragility and consequence functions. Fragility expresses the distribution of physical damage given an intensity measure level. This graph illustrates this point. For any value of observational intensity in the modified Mercalli intensity scale, one can obtain the fraction of buildings that are expected to show one of the 5 physical damage states indicated in the horizontal axis, which range from negligible to collapse. Given one such damage state, a consequence function, as exemplified in this figure, can then be used to obtain the distribution of loss, herein expressed, for instance, in terms of repair to replacement costs. On the right, we can see another example of a consequence function, where the number of buildings heavily damaged are related to the number of fatalities. In other words, vulnerability can be assessed directly as an independent component, or then as the aggregation of these 2 subcomponents. The approach to be followed will depend on the availability of data for the particular region under study. There are roughly 3 categories of methods to develop the corresponding models: empirical, analytical, or those based on expert opinion. When assessed independently, vulnerability is typically based on expert opinion or on an empirical method. One can think of an example of expert opinion as the best estimates given by a group of senior earthquake engineering specialists on the ratio of repair cost to replacement cost for different building typologies. Their weighted mean, based on the experience and confidence levels for each building class, is an expedite way to obtain vulnerability functions that can be used in situations when damage data is not available. However, its reliability in terms of producing realistic estimates of loss is necessarily debatable. On the other hand, this figure illustrates a very simple empirical method to determine vulnerability. It estimates losses, shown in terms of number of deaths, with magnitude from past observations. The drawbacks of this approach are evident, as it doesn't take into account the different levels of shaking across the affected region or the associated distribution of population. Let us now consider the case where each subcomponent of the vulnerability is evaluated. Expert opinion fragility, which again relates an intensity measure level with a damage state, has a questionable reliability but provides damage probability matrices with minimal effort. Empirical fragility is based on the observed damage data, which is then related to observed ground shaking. Ideal sources of data should include all of the buildings in a given area, including the non-damaged ones. Finally, analytical fragility resorts to the application of numerical models to estimate the response and performance of buildings under increasing levels of seismic action. Consequence functions are generally expert opinion based or empirical, and they are used to convert damage to loss, either in terms of repair, replacement costs, or fatalities. In summary, vulnerability expresses the damage and losses conditional on a given level of ground motion intensity for certain assets. Finally, the 3 components, which we addressed separately, can then be combined to calculate the seismic risk, this is, the probability of losses due to earthquakes. This probability can be obtained by calculating the probability of levels of ground motion, that is, the seismic hazard, to which populations or buildings are subjected, defined and classified within the exposure model, and multiplying these by the probability of loss given a level of ground motion, that is, the physical vulnerability. social, economic, or political factors that influence vulnerability should also be taken into account. One of the most relevant global collaborative efforts of the recent years, in terms of providing tools and resources for the assessment of earthquake risk anywhere in the world, is the Global Earthquake Model, or GEM. OpenQuake is the GEM suite of open-source software for seismic hazard and risk modeling. It comprises the platform, which allows users to visualize, explore, and share GEM's datasets, tools, and models, the engine, which is GEM's state-of-the-art software for seismic hazard and risk assessment, and a great variety of modeling tools. OpenQuake allows to assess losses not only for single deterministic events, that is, for specific earthquake scenarios, but also considering all probable events, including classical probabilistic seismic hazard-based and probabilistic event-based risk assessment. The USGS pager, which I mentioned earlier in the context of building inventories, is an automated system that takes in seismic data from remote sensors following significant earthquakes worldwide and provides fatality and economic loss impact estimates within 20 to 30 minutes of the earthquake's occurrence. That is, well in advance of in-situ observations or news accounts, and they can hence play a primary alerting role. Users can also sign up for earthquake alerts for custom geographic regions and magnitude ranges through the USGS Earthquake Notification Service. Other seismic risk tools include the Earthquake Loss Assessment for Response and Mitigation QLARM, which provides loss estimates for scenario earthquakes, that is, which are likely to occur in the future, and loss estimates for earthquakes just hours after they happen anywhere on the planet. Another tool is the Earthquake Loss Estimation Routine, developed as part of an European project, which provides rapid estimation of earthquake shaking and losses in the Euro-Mediterranean region. In short, what are the main points that we can take from this video? Firstly, that the seismic risk is the aggregation of three components, namely the seismic hazard, the exposure, and the vulnerability. The seismic hazard, as we discussed in a past video, is constant in time. The seismic vulnerability, which is the only factor that as humans we can actually try to control, tends to reduce as, fortunately, new structures are usually safer than old ones. However, since the exposure or the amount of assets present in hazard regions can increase very significantly over time, the resulting seismic risk can also grow, overshadowing desirable reductions on the vulnerability. Finally, we briefly overviewed some of the existing software and tools to model and compute seismic risk, or each of its components, which greatly vary in complexity and accuracy. The earthquake engineering community worldwide has been and will continue to resolutely work on these models and on making them available to the public. The reduction of seismic vulnerability must be one common goal of our society. Thank you for watching this video.